All right, let's go ahead and get started. Is the microphone good? Never used the microphone before, so. Okay, so the final exam is this coming Monday at 12 in the Chem 102 building. We'll give you from 12 to 2 p.m. the full time. The length of the exam is about the same length as the midterm, so it'll be about the same amount of work, but we'll give you the full 2 hours rather than like the hour and 15 minutes or hour and a half, whatever there was on the midterm. I think all of the material from the semester is fair game, but I think there's definitely more of an emphasis on the things which we've seen since the midterm. But you should definitely be able to think about things like ID3 decision trees and what is cross-validation and all of that sort of a thing, because that is all carries throughout the whole class. So my plan for the review session was to just go over the two final exams that that we posted, because I think in the last recitation we went over the one from 2016. If some of you were there, hi. Then it might be more valuable for me to start with the one in 2012 and then go over to 2016. Sound good? Okay. Okay, so looking at the short questions problem, problem A from the 2012 exam. Do people want me to go over this question? Yeah? Okay. I don't really like this question. I wouldn't want you to be too concerned with this sort of a thing. But so you all remember this, I think we called them like L of M of N problems before, and so it's the same idea. And so if you have the way I like to think about this is that if you have a whole bunch of features, there are n features. The way that these R of k functions is that for a set of k relevant variables, so we're going to say that this is the set of k relevant variables. If we pick R of them, then that example is labeled 1, and if we don't pick these R, then that set will be labeled with 0. So let's do this. So these are two positive instances of the class when R is equal to 3. And I'm just saying that these features are on, and they're within this K set of pre-selected features, and there are n of them total. So I don't really like the wording of this first problem, where it says, phrase this problem as a problem of learning a Boolean disjunction over some feature space. Define the feature space as the learning problem. So I guess what the idea is, what we're trying to get you to do here is that realize that from this we could create a whole bunch of features which represent sort of the set of possible functions which we could learn. So if we have n Boolean variables, and how many ways are there? How many ways can we select k of them? And choose k? Yeah. So there will be n choose k numbers of features. And oh no, I'm sorry. So there will be. Sorry.
If there's k relevant and at least R of them.
Yeah. Yes, it should be k choose R. So that's the
Number of relevant features.
The number of relevant features. So so if I'm peeking ahead a little bit, so the k there is k choose R because you can choose k of those particular features, but the total number of sets is n choose R, right? we're given a particular K, that's correct. Okay, so okay, let me just try and see if I can work this out. So basically the idea is that I think that we want to figure out what all of the possible different combinations of the Boolean variables. So we could have a set which is x1, x4, and x7. Let's say that r was equal to 3. And we have a whole bunch of these for all of the different combinations, and we want to try and learn weights for each of these to try and approximate the true distribution. And so we should be able to do that because if we look at the data, we'll see which of these combinations match the data, and then they'll get positive weights. I really don't like this K of M of N of N of whatever it's called problems, so I wouldn't focus on them too much. Okay. And I'm not really starting off this review session particularly strong because I didn't know about this bound for the winnow in the second problem, but I looked this up before the review session, and this is just a particular bound for the number of mistakes that the winnow classifier makes, and you can prove it with this particular problem setup. Are there any questions? Yeah. Like what?
On the slide, so like these stuff, you have to remember then how many mistakes like window makes.
Like the old K log N, like.
Or like in general, like this is one example, but like you need to know these.
So like facts, probably not. I don't think we're going to ask you what is the exact bound of the perceptron algorithm, but you should be able to know that you can bound the number of mistakes using the perceptron algorithm if the data is linearly separable. So things like that. So the appendix is pretty thorough, and so you shouldn't need to know all of the particular equations. Let me just move on from this question because I don't really like it. Okay. Okay, so let's move on to B. So is people interested in seeing me work out B? Yeah, okay. So, yeah. I don't know how to prove it off the top of my head, and we're not going to ask you to prove the bound for that, so I wouldn't worry about it. Yeah. Okay, so the problem B setup is a very classic sort of naive Bayes style problem where we give you sort of information about certain probabilities, and we're asking you to reason about particular events. And so it says women who smoke are 21 times more likely to develop lung cancer compared to those who don't smoke. About 10% of total women smoke. If you learn that a woman has been diagnosed with lung cancer and you know nothing else about her, what is the probability that she's a smoker? So they're basically two random variables that we're dealing with here. One is whether or not the person smokes and whether or not they have cancer. And so we're told a couple of things right off the bat. So women who smoke are 21 times more likely to develop lung cancer compared to those who don't smoke. So the way that you can interpret that is the probability of cancer, given that you smoke, is, right, it should be 21 times the probability that you have cancer. Given that you don't smoke. Then it says that 10% of the total women smoke, so the probability of smoke is 1 out of 10. So now we are asked, what is the probability, given that you know that the person has lung cancer, what is the probability that she is a smoker? So what is the probability of smoke given cancer? And does everybody see kind of right off the bat that you don't directly have enough information, well, you have enough information here, but you can't just answer this without doing a little bit of probability algebra. And so these sorts of problems are like the classic Bayes rules problems. So if you remember Bayes rules, you can swap these and you can say the probability of cancer given you smoke times the probability of smoke divided by the probability of cancer. So we're already in a better spot because we know something about this, we know something about this, and then this is just equal to a sum. So before let me just write, I'll write over here what the probability of cancer is. So the probability of cancer, so we have to marginalize over the probability that you smoke. So it should be the probability of you have cancer and you smoke plus the probability that you have cancer and you don't smoke. So now we can use the conditional probability rules to simplify these two things into a form which we know how to deal with. So we have the probability of cancer given that you smoke times the probability of smoke plus cancer, not smoke. Is everybody following so far? Okay, cool. So I think that we can compute that. So we can compute it in terms of, so we're not actually given an explicit probability for either of these two. But we can write this whole thing in terms of one of them. So I think I'll write it in terms of the cancer and the smoke. So this is equal to P cancer. Then we know that the probability of smoking is 1 over 10. Then this is equal to 21 times this. So this is plus 21 P cancer. And then the probability of not smoking is 1 minus the probability of smoking, so you get 9 over 10. Okay, and then I think this can be further simplified, right? So right now I'm only working on the denominator. I think, yeah, so I think I'm okay so far.
21 should be at the top.
The 21 should be here?
Yeah, no.
Okay. Yeah, it didn't look right, because I remember thinking that the math wasn't that bad. Okay, yeah, so this is equal to 21 over 10 plus 9 over 10, the probability of cancer given smoke, right? Is it equal to 3? Is that right? Oh, okay, okay. Yeah, I'm really. So this. Yeah. Okay. Even here? Yeah, because they have to be the same variable. Okay, okay. So then I think what we can do, yeah, okay, so we have, of course, the right 3 in the denominator. And so now we can, given that we don't know what the value of this is, are you sure I didn't mess this up? Because this is supposed to cancel with that. Sorry? Oh, put the 21 here. Right, right. Okay, okay. So the probability of smoke is 1 over 10. and we divide this by 3. This is equal to 2.1 over 3. Okay, we got there. Cool. It's a little bit harder doing math in front of 50 people than it is just when I'm at my desk. All right, anybody have any questions about that? It's just sort of manipulating probability. So Bayes' rule, you should know joint probabilities. You should know how to do marginalization, conditioning.
You're not providing any equation in the appendix, or are you?
I think we're going to give you Bayes' rule in the appendix, but we expect you to be pretty familiar with manipulating probabilities. Yeah. So like going from this line to this line, we might give you that. I don't really know, but you should feel comfortable being able to do that on your own. I think, yeah, I can look at that. Yeah. Yeah. Yeah, that might be a good idea. I'll think about that. I'll have to, I don't know if Professor Roth will get back to me because right now he's in China, and he will be for a while, but I'll email him. I'll email him. Okay. Okay, so moving on to problem C. I think this might be the problem that we had in the midterm. This is just sort of a memorization problem. We tried to avoid asking questions which explicitly ask you to regurgitate something directly from the slides or that sort of a thing. So, but the things that you need to know about pack learning, or I would know the definition pretty well in case this does come up again. But there's also that a post on Piazza where somebody, I think maybe around the midterm time, wrote a pretty good post about pack learning and deciding whether or not something is pack learnable. And I think that post can explain it better than I can explain it right here, and that I would probably help you all more if I could not explain that problem. Yeah. Sorry? So, I mean, I don't really know what to say about C because it's just a definition from the slide. So I'm just saying the things which you should know about pack learning are this definition and the stuff on the Piazza post. I think that if you understand those two things, it would be good. Yeah?
What's the difference between concept class and hypothesis?
So the concept class is sort of so there was some true function which labeled your data, and you are trying to you're trying to find the weights for a particular function which match the true function which labeled the data. But it might be the case that the concept class is more expressive than the hypothesis space. So if you were trying to, this is like not a really great example, but if you had this kind of circle example where the positives are on the outside and the negatives are on the inside, the concept space here is, it has to do with this circle, and it has this nonlinear thing. And you could try, if you limited yourself to the hypothesis space of linear functions, you could try and approximate this function. You do a really bad job, but the possible classifiers which you could learn are defined by the hypothesis space. Does that make sense?
So we give the hypothesis space concept class is what is actually going to be able to do.
Yeah, so somehow this data was magically generated by some probability distribution or some function. That's the true space.
What are the functions that would be good enough to do the job?
Yeah, yeah.
Okay.
Mm-hmm.
Is the hypothesis space a subset of the concept space, or are they not related in that sense?
Is the hypothesis space a subset of the...
Is the concept space a set of functions, or is it just one function that explains the data?
I think it's probably, I think
Or a set of functions?
it's a set of functions. Yeah, it's a set of functions which take a particular parameterized form, I think.
And all of the functions, all the functions in that set have to correctly, I guess, fit the data, separate the data.
No, so like one of the parameter settings from the concept space was selected, and it generated the true distribution. And now we're trying to pick a function from the hypothesis space to try and match that distribution. So I think that there's probably no clear relationship between them. Okay, so let's move on to the support vector machines. Okay. Okay, so for this particular, okay, so what are the things which you all will probably need to be able to know about support vector machines? So I think the things which we've seen in the homework and from maybe the previous midterms are really good, sort of identifying what is a support vector, what does it mean to be a support vector, what happens if you remove the support vector from the training data, and does that change the classifier, and what are the implications of that? What does it mean if the alpha value in the dual formulation of the SVM problem is positive? What does it mean if it's 0? Okay. So do people, yeah.
Are they all, I mean, zeros for the ones that are not support vectors, but the ones that
Yeah.
are non-zeros, they're always positive, right? Or if they're-
Alpha is greater than or equal to 0. Yeah. Yeah. Okay. Should I just draw this grid and we'll try and solve this problem as we go? Is that, okay, I'll just do that. Okay, we have 4. Okay, so we have a positive example at 0, 2. 0, 2. Positive. 0, -2. Somebody just check me as I'm doing this so I don't mess it up and then mess up the whole problem because of it. Oh, this should be a plus. Okay, so I think this is what the data looks like. The plus signs are the positive data points. The circles are the negative data points. Okay, so what is the idea behind the support vector machine? The support vector machine, if the data is linearly separable, it's going to find the linear separator between the positive and the negative data, which maximizes the margin. And so what does the classifier look like here? What does the boundary line look like? I guess it's hard for you. Okay, but it's going to come right through here. And if I actually scaled my graph correctly, then you would see that the distance between these 2 points and these 2 points should be the same. So the support vectors are the ones for which the margin in the hard SVM case is equal to 1. So what does that mean? That means that y times w transpose x. So this is the margin between the data point and the boundary. And when it's equal to 1, these are the support vectors. And so because this boundary is the same distance between these 2 points and the same distance between these 2 points, this is a support vector, this is a support vector, and support vector. Any questions about that? Okay. I think that on maybe the fourth homework, we had a problem similar to this. Okay, so I drew the hyperplane. Now find the values of W1, W2, and B in R that optimize the hard SVM objective. So now we want to find the actual equation for this separator given these particular support vectors. And yeah.
You substituted the x's. Like, how do you know which ones were the support vectors? Like, mathematically, like, you put in the values of x to side. And what is W?
How I knew what the ones where the support vectors were was that I was able to visually look at the plot and figure out where the line would, that would go and separate the data with the largest margin. If something like this, I think this one is a little bit less clear exactly what the line is. If it appeared on the exam, we would make sure that it was like very obvious what the separator was. Like y equals x or something like that. Yeah, yeah, okay. So now we need to find the actual equation for this. And the way that we do that is by using this fact that for the support vectors, this value is equal to 1. And so what we do is that we take these 4 support vectors, we plug in their x's, and then we have 4 sets of equations with 3 variables, and then we just solve that system of equations to solve for the different weights. Does that make sense? I'm not going to solve that system of equations, but does anybody want me to just like explain one of these a little bit more? Okay. Yeah.
Why is it equal to 1 again?
Yeah, because the way that the hard SVM objective looks, we are trying to find on the first page, we're trying to find the minimum value of the L2 norm of the weights such that the margin, which is this thing, is greater than or equal to 1 for all of the data points. And it turns out that when the smallest margin is equal to 1, that's your best value on the objective function. So if this margin had been larger than 1, then you could find a W which had a smaller magnitude, but still separated the data. So it's just the way that the hard SVM is set up, is that we require that the margin is always going to be exactly equal to 1. And so we knew that going in. Yeah. Mm-hmm. Yeah.
What would the update rule for this particular?
So we didn't really talk about that. So we talked about the update rule for like stochastic gradient descent and like these online algorithms and that sort of a thing. I don't think that we've ever talked about the update rule in terms of the support vector machine. Generally, these are like optimization libraries that you go in and you just do this whole thing.
You're not really expected to calculate or write out an update rule?
I don't think so, no. Okay.
So sometimes back in the homework, we only have 2 supporting vectors. Likewise in this question, 3 parameters to solve. And that's, you can solve the third parameter, right?
You can, right? We have 4 equations and 3 parameters.
But sometimes you only have 2 supporting vectors and only 2 equations.
I see. If that appears in the exam, that will not be a problem. Yeah.
In the solution, that W3 is at the bias.
I think, yeah, they changed it to the bias, but it was the, yeah. Or they changed it to W3, but it is the bias, yeah. Okay. So then the next part is still related to this. It says provide the classification rule used to classify an example. And basically, if the way to decide which side of this linear separator a point is on is by computing this. And so if this value is positive, then we're going to give it a positive label. If that value in parentheses is negative, then we're going to give it a negative label. So that's what we were looking for in that particular question. What would the error on your classifier be on the training examples D expressed as a fraction of the training examples misclassified. So this is just basically asking, is the data linearly separable? If it is linearly separable, then the SVM will always have 100% accuracy on the training data. Okay. Draw on the grid the hyperplane that would be produced by a hard SVM when you use all the training examples except 0, 2. So, okay, so if we got rid of this guy, now it looks like the classifier, the largest margin would be something which looked like this, right? On the grid. Okay. Now, okay. So if this is the new separator, and it's asking, will this point be misclassified? And the answer, yeah.
Can you just explain again how you got that to be the new separator?
So it's really just, I kind of looked at the data, and these are the 2 positive points. These are the negative points. These are the 2 which is closest together, and I found that the line that was kind of perpendicular to that.
Why perpendicular? Is that...
Because if I had done something like this, then the margin between them wouldn't have been maximized.
But the margin you get from that perpendicular line seems to be the same margin you had at the original line, right? Yeah. Aren't they like pretty much separated with the same distance, right? Because now that plus is like a margin 1 away.
I do see what you're saying, but okay, so, but it has to separate the data.
Yeah, so the original one was still separated, right?
Why don't we change the line, because that's also like, why don't we just like keep it the same line, because that's still the same margin.
Okay,
Smaller this way.
with the diagonal, it's smaller?
No, with the perpendicular line.
Right, I think with the diagonal, the margin,
Yeah, because the margin should be out, computed by, I don't know, taking the distance of that data point
Yeah.
to that hyperplane. So
Yeah.
it's down to the same point. I have to draw in, like, that's perpendicular to the hyperplane, so. I mean, maybe you could draw it a bit clearer. Margin.
I'm not sure what you're saying.
If you draw the margin of the original line and the perpendicular line, you can see it.
Draw the margin? So you mean the distance here, you mean? For this one, and then for this one?
Isn't it that the distance between hyperplanes, it doesn't matter what the slope of the line is, it just matters what point you're intersecting it with? So if you take it that way, then the original plane should still have the same distance, even if you remove the distance is measured perpendicular to the hyperplane. The more you angle the hyperplane, the smaller the distance gets.
Like in linear regression.
Take it to an extreme and put it at 90 degrees to those 2 points, and your margin is 0. So perpendicular is the largest distance if you're measuring perpendicular to the hyperplane.
Yeah. Just to go through this point.
Otherwise, you're measuring some hypothesis smaller.
Yeah, okay, all right, that's fair. I'm not being able to reason through this right now, but the answer is this vertical line. You know, the more extreme that you get this, then all of a sudden it's not going to correctly classify the data. And it could be that, that the weights which you get for this particular slope are going to be larger in magnitude than for the vertical line. But, okay, but you have to scale the line so that the margin is exactly equal to 1. And then we're trying to find the smallest value of the weight such that that margin is equal to 1. And I think that maybe I am getting confused about how this margin is working, but basically I think that this particular line is going to have a smaller L2 norm, which maintains the distance of 1 between the points than the diagonal line. Mm-hmm.
I think the problem is that people are thinking the margin as a straight line, but the margin is perpendicular to that line. So
Yeah, so the margin to this point is actually here.
so that would be smaller.
Right. Okay, so the distance to this perpendicular line is actually, yeah.
That's smaller than, so you have to have it at this point.
Okay. Okay, good. I'm glad we got that. Okay.
Explain that last part of the summarize. So why is it like this?
So why is it not the diagonal line, and why is it the perpendicular line?
Yes.
So we can arbitrarily scale the weights to make the margin however the size that we want it to be, just because of how linear algebra works, and then we can scale W to, and it doesn't change the sign of the classified points, and so the margin in terms of the SVM thing, it's going to be 1 for both of the lines, but I think that the objective function, which is to minimize this, will be smaller for the vertical line than for the diagonal. Okay, so I think, okay, maybe the confusion is that there are two margins, right? There's a geometric margin where we are just measuring in this Euclidean space the distance between here and here, but then there's also this margin in terms of this particular equation. And so, yeah, so I can, for this line, I can scale the weights to be anything, and it will still define that particular line, but it's actually changing the margin that we use here. So maybe that's where some of the confusion is coming from, is that there are two different margins which we're dealing with. Okay, yeah.
By margin there,
Yeah.
what are you referring to when you say it in the second sense?
In this sense?
Yeah, in the sense where it's always 1.
Uh,
Is that what you're saying, the whole equation there is equal to 1?
yeah, so for just the support vectors, this whole equation is equal to 1.
And the reason why it's not diagonal is because, I mean, if you look at the plus sign there, right, this closest line isn't going to be in line with the negative. It's going to be a closer diagonal with the diagonal line.
Right, but so this is getting to the, I think this still is getting to the confusion that this is you're reasoning about the geometric margin and making that equal to 1, and I think that this is a little bit different because.
The reason why it's vertical is because of the geometric or the second. That's my question.
I see. I think the reason that it's both. So I think that it's this one. Okay. Okay. Yeah. Thank you. Let's just move on. I've really never thought in very minute detail about this, and I can just tell that that's what the line is going to be, and I just never really went in that much detail. Okay. Okay, so the question was asking, if this is the separator, is this point going to be misclassified? The answer is yes, because it was a positive point and now it's on the negative side. Okay, then the same thing for 2 and, so we're gonna get rid of this guy. We're gonna put this one back. And so, that point? Thank you. So this one I can reason about. So what's the separator going to be here? Is it going to change? It's going to be exactly equal to this one because there's still a positive and a negative support vector left. And even though we deleted one support vector, these two are still the case, and so it's not going to change. Okay.
Question. So in the original list of support vectors,
Mm-hmm.
should you put that fourth one?
So in the original list of support vectors, we had, oh, so this is now a support vector again. So in the original list, we have 4 of them. Is that what you're asking?
Yeah, but like in G-define the 3.
No, so the support vectors are the ones which are on, for which this is equal to 1 in the hard SVM case. And for all 4 of those points, it was equal to 1. Yeah. Okay.
Can you explain why we can't, it's the same conversation we just had, but like why we can't just use the vertical line to separate when we remove 2 of these support vectors?
When we've removed this one? So that we put this one back.
Oh, okay.
Yeah, okay. Okay, what will be the average error if you use 6-fold cross-validation on the particular training set? Okay, so I guess this question is really getting you to reason about, if you remove each point, does it make an error? So we already saw that if we remove this point, there is no error. There is an error here. Will there be an error if we remove this point? No, because it's not a support vector, so it doesn't actually change the margin. If we remove this, this is still a support vector, so the margin is not going to change. The same thing for this one, and we won't receive an error here. Oh, yeah. If I remove this one, then the margin's going to be that straight line, just because I know it is. Yeah. Okay, so there will be 2 errors. Yeah. Yeah.
Sorry, could you just quickly explain, like, what was the reasoning between 3 and 4 and how they're different?
Okay, yeah, so.
Most times, like, what I'm confused about is that in both 3 and 4, you're removing a support vector. So why does one of them have to remove this one?
So in the first case, we removed this one. Then these are the 2 points which are closest to each other, so we put the margin in between. And it still linearly separates the data. But then if we remove this one, we still have to classify the problem correctly, and so we still have to use this slope. Okay, so if we got rid of this one, if we moved this, this would decrease the value of the margin in either direction. Okay, so the soft SVM formulation. Okay, this isn't the soft SVM formulation that we've seen. Yeah.
This might be kind of a weird question, but like with the 6-fold cross-validation, why are we removing exactly one each time?
Because, so the way that the cross-validation works is that if you have n data points and you're doing k-fold cross-validation, you divide each of the points into n over k buckets, and then you hold one out and you train on the others. And in our case, n and k are both equal to 6. And so each time we're holding one data point out and training on the other 5. Mm-hmm. Yeah.
And in the solution, why the error each time is 1 over 6?
Because
Every time you invoke the train data is only 5.
so I think the average error will be 1 over 6. The error will be 1 over 6. All the cases error will be 0. Yeah, I agree with you. Yeah. Basically, will be the average error. Okay, so it's not. I think the question is not fully specified. I think it should say it's really asking what is the average error on the full training set if you run cross-validation. So you train on 5, but then you still evaluate on all 6, and you calculate the error on that. And I think that would produce this answer. We've done our best to make sure that there are not ambiguities like this on the final. Okay, so like I was saying about the soft SVM objective, this is not the form which we have seen, but they're equivalent forms. Yeah?
Wouldn't you make just one mistake? There's 2 mistakes they would make. So wouldn't that be, both would be 1/6? Why is 1 2/6 and 1 is 1/6?
Okay. The soft SVM objective, this is not the one that we've seen, but they're equivalent. So the way that, So I'm just going to write down the soft SVM objective, and then I'm going to kind of reason about each of the two terms, because I think it's useful to be able to kind of understand the interpretation of both of them. So we want to. Does anybody want me to spend time to talk about how this is equivalent to the definition that we see in class, or should I just switch to the definition that we see in class? We're okay with this? Okay. So this is exactly equivalent to the definition that we've seen in class. And so the problem 2 is asking for how, basically the problem is getting at if when we change this constant, this hyperparameter, how does it change training? And so the way that you can interpret these two terms here is that one of them has to do with the accuracy of the classifier on the training data, and the other one has to do with the regularization term, which is trying to encourage a simpler model. And so this is the term which has to do with the accuracy on the training data, and this is the regularization term. So if you think about if this term didn't exist and this value is C, what is the value for W, which is going to actually minimize this function? It's just going to be W equals 0, right? The 0 vector. Because the only thing that we care about is minimizing this one. And so this term is really trying to bring the weights closer to 0. Alternatively, if we look at this one and we didn't have this term, then the only thing that we would care about is trying to make sure that the margin for this particular problem is as large as it could possibly be. And so we don't care what the values of the weights are, so we could set them to really extreme numbers to be able to fit the training data. And so this is really focused on the accuracy of the SVM for the training data. And so the question is asking, for what positive values of C will the hyperbeam produced by the soft SVM objective produced by the hard SVM? So the hard SVM, we know that if the data is linear separable, it's going to separate the data perfectly, and it will always do that. And so if we increase this value of C, we're putting more and more weight on the training data accuracy, and we're forcing the model to be as accurate as possible. And so as C gets larger, we put more and more emphasis on the training accuracy, and so then it's going to be the same. It's basically forcing the accuracy to be 100%.
What's regularization?
Regularization, so I don't think we saw it too much in this class, but it's basically encouraging the model to have smaller weights, and because we're trying to minimize this function, so as the weights get larger, this value gets larger. And so this is encouraging the weights to be smaller, and when you have smaller weights, it turns out that the model is simpler. Yeah.
So we always try to have smaller weights, but to have that higher accuracy, sometimes we compensate with higher weight.
Yeah. So sometimes in order to get higher accuracy, you need to increase the value of the weight, but that might lead to overfitting on the training data. And so this is trying to prevent that from happening. Yeah.
I could be wrong, but isn't the hard SVM formula just minimize half of U squared?
But you're forgetting about the constraints. Yeah.
What are the constraints again?
The constraints in the hard SVM objective are on the other page. So it's basically the slack variable goes away in the soft SVM case, and when we set C to be very, very large, we don't really care what the value of the slack is, and we can set it to be a huge number. Yeah. Okay. Okay, yeah.
See one, there's right stuff, then it's a circle, and they're not, so that's like, I thought what does it mean?
Yeah, it just must be a typo on this exam, yeah. Okay, so moving on to probability.
Do we have any constraints on this equation or no, that's enough?
So I think that the constraints are sort of baked into this in some weird convoluted way. So, all right, so I think that'd be worth talking about. So the original, I think that the original let's do I. So I think that this is what the second term looks like in the soft SVM case, and we have this, this slack variable, and we require that the margin be greater than 1 minus the slack variable. So as the slack variable increases, it's really, really easy for the model to be able to separate the data. And I think the way that these two things relate is that if you solve this equation for this slack variable, you'll get 1 minus this value, and then because we know that the slack variable must be greater than or equal to 0, we can substitute this max in for there. So it has to be the maximum of this value, so it's going to be 0, or it's going to be this 1 minus the slack variable. So I think that these two things are equivalent, so the constraints are sort of baked into that. Yeah. Mm-hmm.
Are we minimizing?
You're minimizing the entire thing, yeah. Mm-hmm. So I think you saw a problem like this in the most recent homework about converting from something which looked like this or into something which looked like that and vice versa. But I think this is the more standard way to see the soft SVM objective. Okay, so for probability questions. Okay, so I probably won't go over the problem A in detail. This is just saying we're not given a model, so we aren't given a graphical model, we're not making any independence assumptions, and it's just asking for the probability of seeing these particular events. And the way that you do that is you count how many times that event occurs in the data, and you divide it by the total. So I don't think it's worth me talking about that one. Okay. So consider the following graphical model M over the three variables. So we have M, and it's equal to A, B, C. Okay. We even back up a step. So does everybody understand what's happening with this graphical model? Like, what are graphical models? So when you have 3 variables and you want to define a probability distribution over the joint of all 3 of these variables, you can do it with a large number of parameters, but that's hard because they're hard to estimate the good values of the parameters from the limited amount of data that we have. And so sometimes we make independence assumptions about these random variables. And what these Bayesian networks do is that they encode these conditional independence assumptions within the structure of the network. And then instead of estimating parameters for the full joint for A, B, and C, we can estimate them based on the structure of the network. So generally, when you see something like this, the first thing that you should think about is how does the joint probability factor according to this graphical model? And the way that this works is that you multiply all of the probabilities of a particular node given its parents. And so A has no parents, so the joint probability of A, B, and C under M is equal to the probability of A times the probability of B given A times the probability of C given B. Okay. So if we estimate these 3 probability distributions from the data, then we've done what's called parameter estimation for this particular graphical model. And so what are the things that you need to estimate for this, well, we need the probability of A is equal to 1. The probability that, so let's assume that these are all binary variables. So we'll need to do the probability that A is equal to 1. A is equal to 1. We don't need to do 0 because it has to sum to 1. Then for this, there are two different probability distributions that we need to know. We need to know what is the probability that B is equal to 1 given A is equal to 1, and what is the probability that B equals 1 given A is equal to 0. And the same thing for this. So these are two different things which we have to estimate. They do not sum to 1. Yeah?
That's 1, 7, and 11 in the...
Sure, yeah. So you can read them off. Okay, so then it says using the data in that previous table, estimate these probability distributions. And the way that you do that is for A, you'd count the number of times that you see A is equal to 1 divided by the total. And the same thing here, but you have to condition on the value of A and that sort of a thing. So you have to do this for 7 different probability distributions. Is that clear? Okay, cool. And as somebody pointed out, there's a typo on this. The last one should be 1/6 and not 1/3, which means that all of this math gets messed up. So, okay, so this is a part where you all should be able to manipulate probabilities comfortably. And so the question is asking, under the model, what is the probability that A is equal to 1, B is equal to 1, and C is equal to 0. So you can't just read this directly off of the table as we did in the very first problem, because now we have these conditional independence assumptions. And so the way that I sort of approach these problems is that this is asking for a joint. We've written how the joint decomposes over there. And so this is equal to probability that A is equal to 1, probability that B is equal to 1 given A is equal to 1, times the probability that C is equal to 0 given B is equal to 1. And so all of these terms are things which we estimated in the previous problem. And so you plug in those values that we estimated from the data and you simplify. So I won't do that. So 2 and 3 look to be identical, but just with different parameter values. Okay, so then the D is a little bit different. And so it's asking, so what is the probability under M such that B is equal to 1? And so the way that you can do this is that, so the way that I approach these problems is that this is equal to the sum over A in 0, 1, the sum of C in 0, 1, the probability of A, B is equal to 1, and C. Then this, okay, did everybody see how I did that? This is just marginalizing over those values. So I wrote out the joint, and I only care about the probability that B is equal to 1, so I need to sum all of the values for A and for C. And so this can decompose into this times the probability. And we have these two sums, sum over A, sum over C. Neither of these two terms depends on C, so I can push the summation for C into here, and then the sum over C here is just equal to 1, so that's actually just going to vanish. So I'm going to get rid of this. And so now we're left with exactly what the solution has here. So we have these terms. There's going to be a term, these pair of terms for each A is equal to 0 and A is equal to 1, and then you read them off of the previous problem and you plug it in and solve. Okay, should I do 2 and 3, or are people bored of this? I kind of see some. Do 3? Okay. Yep. So number 3 says.
3 uses 2. Basically, the solution to 3 is 1 minus 2.
Okay, but it's important. I want to at least talk about there's an intermediate step there. Okay, so we're asked what the probability of A is, but what is the probability that A is equal to 0, given some information about B and C. But we know that because of the structure of this graph, that if we know the information about B, we don't, and we're asking about A, we don't actually care what C is. And so we can actually just drop this, and we just look for what is the probability that A is equal to 0, given that B is equal to 0. And if you understood problem 2, then it's just very similar, yeah. Mm-hmm.
So on that equation right there, they get rid of the PC given B.
P of C given B, yeah.
Because it's going to be 1.
Yeah.
So I didn't get rid of that, and it's not going to be 1 because the graphical model doesn't really represent the table, right?
So it has to be 1 because
I know it has to be, but that's because that's an assumption that the table is matching the graphical representation.
No, I think that's kind of a definition of probability. So if we move this sum in, and we say the sum over all the values of C, the probability of C, given anything, this value is going to be equal to 1.
Yeah, that is true, but that joint probability distribution,
Yeah.
without having the graph, would be just P of C given B and A. From like the joint probability distribution without having the graph. So the graph is assuming that P of C given B is the same as P of C.
Oh, okay, yes. So the way that I went from this joint to that equation is defined by the graph.
Yeah, what I'm trying to say is that if you, I guess I'll do it later.
Okay, but so, okay, but let me just clarify. So the way that I went from this joint probability to this is based on the graph, but then after that, it was just normal probability
No,
math.
I agree.
Okay.
I'm just saying that graphical representation doesn't match the table, so if you do P of C given B,
Oh, yes, and that's because of the conditional probability independence assumptions, which the graphical model asserts on the data.
yeah, so what I'm trying to say is that if you don't get rid of that,
Yeah.
I agree that you should get rid of
Uh-huh.
1, but it's not 1 because it's not representing the table.
Great.
If that last term shouldn't be P of C given B, should be P of C given B and A.
Okay.
In real life.
Yes, yes.
Not in-
If we didn't make conditional independence assumptions, yes.
So I'm saying that assumption is not true for this table. That's what I'm trying to say. So if you don't get rid of that, you get a different answer. Then you get rid of it.
Okay. Okay.
So would it be fine if we use that and don't get rid of it and get a different answer? Would the answer still be fine? In the exam. So I agree that you should get rid of it, but if you don't get rid of it, you should have the same answer.
If you, yes. Oh, okay. I understand what you're saying.
If you don't get the same answer, the answer I got would be still acceptable.
If you get the same answer, the same numerical answer,
You don't get the same answer.
then you did it wrong. I mean, maybe you could talk about it, but like, okay, because there's a definite answer to this question. Yeah. Okay, so does anybody have any questions about that? Okay. Yeah. Yes. So we can read that probability assumption off of that graph, because if we know we know B, then A and C are separated. So you can kind of think about it like the flow of influence from A to C is blocked because we know what the value of B is. But we know that, we know the value of B. So if we know that B is 1, then knowing what the value of A is has nothing to do with the value of C because of how this decomposes. So because we can decompose the probability distribution in this way, the only way that we care about the probability of C is if we're given B. And so if we're given A, it doesn't actually give us any more information if we also have B. Okay. So moving on to naive Bayes, it's all very similar to this probability stuff. So we're given this whole set of data, and then we're asked to select the parameters from the table Okay, so let me first talk about the naive Bayes probability assumption. Okay, so just got to talk about naive Bayes and not this particular problem yet. So given some x, so we'll have the feature x1, x2, and then given some label y, we want to assign a probability to this observation. So these are the features for one particular instance, and this is the label for that particular instance. And so what we could do is that we could specify a parameter for every single possible value of these. So if everything is binary and we were trying to explicitly model the joint, there would be 2 values here, 2 values here, 2 values here, and there would be 2 to the 8 values and then -1 parameters. And so that's a lot, and we would like to try and reduce the number of parameters so we can get better estimates from them from the data. And so what naive Bayes does is that it makes a particular assumption that the probability of observing a feature given the label is independent of all of the other features. And so what that means is that this is equal to the probability of y times the probability of x1 given y times the probability of x2 given y. Right, so learning something about x2 does not impact our decision about what x1 is in this particular model. Okay, so if we're given this data, we have 3 features, x1, 2, and 3, and we have this yield, which is the label. We have to pick from this table which of the parameters we need to estimate from the data. This particular table has duplicate parameters that are not independent, and if we have something like this on the exam, we will have removed any of the dependent variables. So what I mean is that 1 and 2, which is the probability that xi is equal to 1, and the probability that xi is equal to 0. These are dependent parameters because they sum to 1. So if we know the value of one of them, we automatically know the value of the other one. So if we have a problem like this on the exam, there won't be any confusion and you'll only see one of them. Okay. Okay. Okay, so the things which we need to be able to estimate from this data is very similar to what we saw before. We need to estimate the probability that y is equal to 1. We'll get probability that y is equal to 0 for free. Then for each of these, we need to know what is the probability that xi is equal to 1, given that y is equal to 1, and the probability that xi is equal to 1, given that y is equal to 0. And these are the things which you should select. Yeah?
Is the answer wrong, the answer key? Because I think you only need either 3 and 5 or 4 and 6, but not all.
Yeah, so that's what I mean by saying that there's some that are dependent, but we're not, you will not encounter that problem on the final, so, but yes. Okay, so then one thing which is useful is to be able to count the number of parameters in this particular model versus modeling the joint directly. So before we said that there were 2 to the 8 minus 1 parameters, 2 to the 3, nobody caught me, 2 to the 3 minus 1, which is 8 minus 1. Here, how many parameters will there be? Just 1. For this, how many parameters will there be? Also just 1. I shouldn't do equals. And the same thing for here. So for any particular feature, there are 2 parameters because we need to estimate the parameter for the different values of y. There are 3 features. Okay, so the problem changed. So now we have x3. Okay, I've mixed examples. So I started off with x1 and x2, and I was doing this for just x2, but this has x1, 2, and 3. So if we pretend that I did this for x1, 2, and 3, there are actually 2 to the 4 minus 1 parameters, and over here, there are going to be 2 per feature because we have to estimate 2 different parameters for the labels, and 1 here So it's going to be 2 times 3, because there are 3 features, plus 1 is equal to 7. Did everybody see how I did that? I moved kind of quickly. Any questions?
Wait, why do you have 2 parameters for the second example, but only 1 for 6?
Here?
Yeah.
So are you asking what's the difference between this and these two?
No, I was asking what's the difference between the first example you did with the 3 parameters and the second example with the 4. Yeah, when you added x3 into it.
Oh, so when I added x3, I was trying to say the probability of x1, x2, x3, and y.
Yeah.
And there are if each of them is binary, there are 2 to the 4 possible assignments of these. And so there's 2 to the 4 minus 1
Right.
parameters. And so this example is more relevant to the problem here.
No, I was confused about the conditional. How do you get 2, why do you need 2 independent parameters for your conditional?
So for these, you mean? So there's, maybe that made it a little bit more confusing. So for each feature, you have to estimate the probability for y is equal to 1 and for y is equal to 0.
Right.
Each of them has 1 parameter because these two do not sum to 1. So the probability that xi is equal to 0 and y is equal to 1, these two things sum to 1, but these don't. And so you have to estimate this parameter and this parameter.
Okay.
Yeah.
Why is the minus 1 there?
Because when we're directly specifying the joint, we have to, there are 2 to the 4 possible labelings, and because the probability of each of these events must sum to 1.
Oh,
Yeah.
yeah.
Mhm. Yeah.
What are you talking about? 2 to the power of 4 and then
So, so if we don't make any independence assumptions, we have to consider, if we make no independence assumptions about this data, we have to assign a parameter value for every possible value assignment to this. So we do the same thing over here. For every possible value assignment, we have a parameter. But when we do it here, it's much larger because we have a whole bunch of things. So imagine if we had probability of A given B, C, and D, if they're all binary. This still has 2 to the 4 different settings for the parameters. Maybe that last part was confusing, but okay, but did I answer your question? Hopefully, yeah.
Can you just explain the minus 1 part again real quick?
Yeah, so think of it, if we're flipping a coin, and we have the probability of heads, or the probability that the, let's just say C is the coin. It's head. If it's 1, it's heads. If it's 0, it's tails. There are 2 possible outcomes, which are 0 and 1, and we need to assign a probability score to each of them. But we know that if that is equal to P, we know that P and whatever this is must sum to 1, and so this is actually equal to 1 minus P. And so this value is dependent on this one. Once we know this, we know this. In this particular case, once we know the 15, we already know the 16th. Yeah. The solution to B is 7 because it's asking about the naive Bayes case. It's not asking about the case without any joint parameter assumptions. So under naive Bayes, you need 7 parameters for this data. Okay, so write explicitly the naive Bayes classifier for this model as a function of the model parameter selected in A. So the probability. Okay, that's one way to do it. So I think that we've seen this done a couple of ways. Okay, what I think I would have, terms. Okay, this is one way to write. So if you all see the solution, this is one way to write the naive Bayes classifier. But what I think that we've seen most in class is that we'll say output y equals 1 if, and then we have this, this fraction, right? So we'll say if the probability, so I'll use all of the features. So let's index into the features with I, so the probability of xi given y times the probability of y, y equals 1, times this, xi given. So what this is saying is that the naive Bayes classifier is going to compute these two values. The top one has when y is equal to 1. The denominator has when y is equal to 0. If this fraction is greater than 1, which means that the naive Bayes model, which we estimated, assigns a higher probability to the instance when the label is equal to 1, then we're going to output 1 as the value. And so when it says to write it in terms of the parameters that we estimated, it's taking this and it's substituting the value which is in that table, like the alphas and the betas and that sort of a thing. It does have one trick, which is nice when you're trying to combine a whole bunch of things into one equation. So unrelated to this problem, but if you say the probability of x equal to 0 is equal to alpha, and the probability that x is equal to 1 is equal to beta, you can say that the probability of x is equal to alpha to the 1 minus x times beta to the x. And these are equivalent. And so that's what the little algebra trick is there. Just to combine them into one kind of more compact equation. Mm-hmm.
In the solution, where does the v and y minus v come from? Like in the last line of the solution, it says v times beta, and then pi from 1 to 3. I don't see that v at the top in the time.
Yeah, I don't know where the v comes from, but it has to do with the prior probability, so I think you can kind of see what they're getting at. It's sort of representing the probability that v is equal to the value v.
Can you somehow use the expression in the line before that and use like argmax on that? Like,
Yeah, so that's another way to put it. So that looks like, what you're describing looks like the decision rule in E1. Yeah.
And you could just put argmax.
Yeah, so that is equivalent to this. Yeah. Mm-hmm. Okay, write the expression for the log likelihood of the entire data set using the parameters that you defined in A. Okay, so so does everybody kind of have an understanding of what the likelihood means? So given a set of observations and some fixed parameter values, what is the probability of observing all of these observations under these parameter values? And so let's say it looks like what it's saying is that we have this data set with m examples. And so the likelihood is if you take the joint of the probability of seeing x1, let me do it for this particular example, xi. So this is the likelihood equation, this has nothing to do with our particular problem yet, other than the fact that there are 3 features. But the likelihood is just the probability of seeing the data, which is this xy, under our parameters. And so one thing that we like to do, because it makes the math easier, is that if we take the log of this, we can push the log into the summation, and then we'll have the log of this particular probability. Then, since we are assuming that this is modeled by naive Bayes, we can use the conditional probability assumptions, which I've written over here, and decompose that. Mm-hmm.
In the actual exam, if we're running out of time, like how important is decision fatigue? Because like this will probably take a really long time.
So we've tried to set it up so that the math is not challenging, right? So we don't want you to have this problem where, you know, I think a lot of people had issues on the midterm with the ID3 decision tree, and so we've specifically tried to not have that happen this time. So, but that being said, I think that if you're running out of time and you're getting, you know, you're trying to rush through the exam, if you write out, so I would give the vast majority of the credit if you wrote, so this doesn't actually have any data for which but let's assume that we had some data that you were going to do this with. I would give you the majority of the points if you wrote out the full correct decomposition of the log likelihood. And then if you made a mistake or you didn't have time to do the actual put in the numbers and that sort of thing, you know, I might just take us like 1 or 2 points off. Because out of 5, I would prefer to do 4 out of 5, but yeah, makes sense.
Because here it says we can easily write this off.
I think you're reading into the word, I don't know.
It is trivial.
In some sense, it is trivial to write the log likelihood equation.
Once you have the previous one, right? You're just taking the log of that.
Yeah, yeah. Okay, we would like to train a naive Bayes classifier on S to help us predict. Okay, what is the decision rule? Okay, these things are different names for that. I would kind of consider this a decision rule, but what they have here is exactly equivalent to selecting which one gives you the arc maximum. Okay, and then predict a yield for the following farm using the decision rule written earlier. And so we have particular features. We're going to plug them into this equation, and we're going to see which y gives the larger value, and then that'll be the answer. Okay, does anybody have any question about naive Bayes? Yeah?
2 questions. One, when do we know we're supposed to use Laplace smoothing?
So like here you get 0.
I think we have it. So we say one way or the other. So we'll say use Laplace smoothing, or we'll say don't use smoothing.
So in here, they didn't specify, right?
They didn't. So I think in general, the default is to not smooth. So if they don't say it, you just do that. But I think we've made it clear that is one way or the other. We were explicit on the exam.
Okay, and second, you're going to go over smoothing?
Yeah, okay. Mm-hmm.
Secondly, what's the difference here between part C and then in E, part 1? They're both, like, what's the difference between the classifier and the decision rule? Like, they're very similar kind of thing.
Yeah, they are, and I don't really, there seems to be some nuanced distinction, which I don't fully understand. But we've made it explicitly clear on the exam what we want you to do. Yeah, I mean, so if you understand these things, that's really the important part. Yeah, we put in a lot of effort to try and make the exam as unambiguous as we can. However, now that I'm saying that, I'm sure a lot of you will find ambiguity in all of the questions. Yeah.
Can you explain the denominator here? I know it's just the probability of evidence.
Oh, so these are different things. So this is just sort of how, so if you're given a point, you're given an x, and you need to decide which y. So this is like the odds ratio. So this is saying when what is the value of this when y is equal to 1? What is the value of this when y is equal to 0? And whichever, if that fraction is above 1, that means that this one is larger, so you should output y. This is not asserting this is not trying to say what is the probability of x. This is not equal to that. And I think that's what you might be confusing it with, yeah.
I'm not quite understanding the difference between the format that we learned here and the one that we derived in C. If we had given the format that we had on the board, would we also have gotten points for the classifier? Or must the classifier be in this one?
So it looks like what C is saying is what is the probability that y is equal to a particular value given the observations. Just if we just look at that first line, it says what is the probability that v is equal to some value given some set of observed features. And then, so that's what that's really written down is the probability of y given x. And then what we write below is the argmax over y of p of xy. So
that's E part 1.
this is E.
Okay.
Yeah. Yeah. Okay, so there was a question about smoothing. I can go over smoothing. All right, let me make up.
Can we just do part E2 with smoothing?
Oh, is there smoothing?
There is. That way we just have a reference.
Part B2?
Or E2.
E2.
If it were to be smooth.
Oh, if it were to be smooth. Okay. Sure. Okay. So in this problem, it doesn't, okay, so okay, I think it might be clear. So actually solving 2, that part doesn't necessarily, okay, I think that if I describe how smoothing works, then you can apply it to that problem. Yeah, I just don't think it'll be as clear. So let me try and make up an example on the spot and see how I do. Okay. Okay, so let's pretend, okay, I don't really care what the rest of this is. So let's just say there's like a 1, and 1, and that's 1 and 2. Okay. Yeah, that'll be good. Okay, so for smoothing, so okay, the idea behind smoothing is that if you are trying to estimate one of these probabilities, so you say what is the probability that x1 is equal to 1 given y is equal to 0, if you never see the pair xi is equal to 0, y is equal to 0, if you never see that in your training data, that probability is going to be estimated at 0. And so if you have an xi and the value is equal to 0, you are never going to output y is equal to 0. And we don't like that because we want to have some uncertainty in our data. Our data is never, okay, so that's sort of the intuition behind why we do smoothing. That's the problem that we're trying to solve. So let's assume that this is what our data set looks like, and we want to smooth the probability distribution of x1 given y is equal to 1. So let's just say y is binary, and x can take on these 3 values, 0, 1, and 2. So if we just estimate the data kind of under the multinomial distribution assumption, which we've been doing where you just count the values. So we say that the probability of x1 equal to 0, given y is equal to 1, is equal to the number of times. So let me say count 0, 1 divided by. So I'm abusing just kind of making up this notation on the fly. But what this is saying is you count the number of times that x1 is equal to 0 and y is equal to 1, and you divide it by the number of times that you see y is equal to 1. So C1 is equal to the sum of x in 0, 1, 2 of Cx1. Right. And so for our particular data set, this is actually going to be 0 over 2. For probability x1 is equal to 1, and y is equal to 1, that is equal to 1 over 2. And the same thing for x1 is equal to 2. Great. Done no magic so far, right? This is just the counting. So what happens when we do smoothing is that we are going to pretend that we saw a new count. We're going to pretend that we saw each feature, x1, lambda times. So if we just say that with Laplace smoothing, we say lambda is equal to 1. So below, I'm going to write the data, which we're kind of hallucinating. We're pretending that it exists, but it doesn't actually exist. So for each point, for each value that x1 takes on, we're going to pretend that we saw it exactly one time. So this is going to be 0, 1, 2. And now we re-estimate these probabilities with this full data set. And so what happens is that the probability that x1 is equal to 0, given y is equal to 1, is now, if we pretend that the count, so what happens when you make things up on the fly. If we pretend that the count is only in the original data set, and then we pretend that we saw it lambda times, this is now our new numerator, but we've done this to all of the count values, and so we need to do this here, which means that this numerator now has to have a 3 by lambda, all right? So if you directly count on this new data set with the hallucinated thing, you should get the same thing. Are there any questions about smoothing?
Do we also have to apply smoothing to the prior probability?
You can smooth the prior probability if we will explicitly tell you to do it or to not do it on the exam. So, but if you smooth the prior probability and you smoothed it by lambda equals 1, so when you compute when you are estimating the prior, you don't actually care what any of the values of x are. So it's sort of like we hallucinated a count for y, like we just hallucinated 2 more examples if we smoothed by y is equal to 1. Yeah. Mm-hmm.
Can you explain why you had 3 lambda to the denominator?
I added 3 lambda to the denominator because so if we add, okay, so all of these counts, these numerators, they have to add to 1. And there are 3 of them. So maybe if I write it out more explicitly, it'll be clear. So the denominator for these things is C of 0, 1 plus C of 1, 1 plus C of 2, 1 without smoothing. Right? So you pick one of these and you put it up here, and you're going to get the probability distribution out. And now what we're saying is that we're adding lambda to every single one of these. And so if we add lambda up here, we're going to add a lambda to all of them.
So it's just lambda times the amount of...
Lambda times the number of values that whatever you're smoothing can take on. Yeah. Mm-hmm. Andre?
I thought like in the slides, like define Laplace smoothing as
Yeah.
like m is like the number of labels.
Yeah, so
that y
people...
will take, or
so people were having trouble. I think that I would not try to understand smoothing based on a formula. I think that if you understand smoothing based on this, then you can apply it to any situation where you have to do smoothing.
But I would think like, because y takes two values, I would have done 2 lambda.
Yeah, so that would not have been right, because if you're adding a lambda to each of these counts, you no longer have a valid probability distribution because they're not going to sum to 1. Okay. Okay, so the next set of problems is the expectation maximization section. So I believe Professor Roth said explicitly that we're not going to ask you to derive the update equations for expectation maximization, which is what this problem basically goes through. And so I think that I'm going to skip this particular problem because I don't think that it's going to be any value to you all for the exam.
So what kind of problem?
Yeah. So I think for EM, you should know that it is a semi-supervised algorithm where you can use, it works on data which is missing, it works on instances which are missing some data. So you have a hidden variable and you don't actually observe that when you get your data set, that column is missing. And so that's the situation when you use it. On every iteration of EM, the, what is it called? The marginal likelihood is guaranteed to go up. So in EM, so if X are the features which we observe, and Z are the hidden ones, what we care about modeling is the probability of just the X, where we marginalize over all of the Z's. And so with EM, every single time you compute the expectation and you do the maximization, you're maximizing this value, and that's guaranteed to not decrease on every step of parameter estimation. So every time you're getting closer and closer to like the true value. Mm-hmm.
So we don't need to do any computations for EM, is that what you're saying for the exam? We just need to understand in theory how it works?
Yeah, just the basic idea is that this data is missing. What do you do when the data is missing? Well, you kind of use your labeled data and you predict values for the data which is missing. But you won't do it in a hard way, so you won't say, oh, the probability of this, or this label is exactly equal to 1. You'll say this label is equal to 1, sort of with probability 0.7, and equal to 0 with probability 0.3, and you learn a new model with that.
Does that mean the EM problem on the other exam is also not relevant?
Mm-hmm. Yeah, it's very similar to this one, yeah. So if you go through the math, this is asking you to compute kind of what is the probability of Z given X, and then this is the E step, and then when you maximize this by taking the partial derivative with respect to the parameters, that's the M step, and doing the math to derive the equations for both of those is, we're not going to ask you to do that.
So can you clarify like what's the range of EM that we're going to reveal?
Basically, the things which I mentioned is that it's semi-supervised. Yeah, so you should just know what EM is and when is it useful. Mm. Okay. Okay, so I have finished that exam. What do people want me to do to go on to the next exam? To take questions? Yeah. On the 2016 one? Okay. Okay, so the first question on the 2016 exam is a naive Bayes problem where we are assuming that the probability, these probability distributions are distributed according to a particular known probability distribution. So in normal, okay, so what does that mean? So before, when we were doing naive Bayes, there were discrete values that the x's could take on. And so what we did is that we assumed that they were distributed from a multinomial distribution. But now what do you do if the probability of xi given y is equal to 1, and xi can take on any real number. So it could take on the number between 0 and infinity. And so we can't directly apply the multinomial distribution because there aren't discrete things which we can count and take the probability of. And so what we do in this particular problem is that we say that for, so we say that the probability of x1, let me just rewrite this. Probability of x1 equals x1, given y is equal to y, is distributed, I believe that's the geometric distribution. And so we say this is y, 1 minus theta of y, to the x1 minus 1 for y is equal to a and b. Okay, does everybody understand what that means? Yeah.
This may sound stupid, but is that y exponent or is that y?
Okay, yeah, so this is not an exponent. So these are two different parameters for each y is equal to a and b. And so it actually looks like this.
How do we know when it's exponent and when it's not? So like, is it quiz, last quiz, and if you do the last quiz log likelihood, you consider those exponents?
Yeah. I think it's just from an understanding of the problem because it doesn't, because if it was an exponent, then it would be asking for theta to the a, and that doesn't really make sense. But yeah.
But what if the labels are like ones and ones? You still like do the same thing, right? Doesn't matter.
That's true. I think that if it was ambiguous and it could be interpreted that way, then I don't think that it would be written in a way that would be, yeah, ambiguous. Okay, so this is the geometric distribution. And then for the other one, it was distributed from the exponential distribution. So probability of x2 equals x2, given y is equal to y, is equal to lambda to the y, e negative x2 times lambda y. Okay, so the log. Okay, do you want me to do the log likelihood part, just the whole problem?
Just like,
The parameter estimation part?
I guess, how do we know the log likelihood the data is going to be that topical? Like, they go to
Okay, all right, so I'll go through that, yeah.
I have a question about, like, at the top when you say log likelihood and it puts like 6 terms.
Yeah.
Like, I thought you would only need 3 terms, or you would write it in that format where you have like an exponent of, you know, x to the x1, and then the other one to 1 minus x1, because,
Yeah.
I mean, gamma is either A or B, but it won't be A and
Yeah.
B, so why are you summing all the values of that?
So it's sort of like, I think the math for this one was not particularly clean to do with that 1 minus y thing, because you can't do that because y is an A or a B, and so you can't actually incorporate that. So basically what the summands are doing is that they're separating the data into A labels and to B labels, and instead of doing it in one giant sum.
But it's correct to still write like gamma A plus gamma B. Because you see my confusion, like why do you need to write the 6 terms?
Mm-hmm.
Some of them would not, it cannot be both true.
Okay, because we're doing it for a whole data set. So we have the data set that we're working with is D, which is a set of examples, and it's equal to D of A. It's the set of examples which are labeled with A, and the set of examples which are labeled with B. And so we have to write one equation, which is going to give us the probability of observing all of D. And the easiest way to do that with this math notation is to separate them into sums over this and sums over this.
Some proportion that is gamma A and some proportion
Yeah.
that is gamma B.
Yeah.
Okay.
Okay. So, is that? Okay, so the question is, what is the, how did they come up with this log likelihood equation? So if I'll rewrite the log likelihood equation that I had over there, which was if you sum over all of the instances in D, under the naive Bayes assumption, we have the probability of yi times the probability of x1i given yi times the probability of x2i given yi. Forgot the logs. So we log, we add, log. Okay, so this is the, so without really paying attention to this particular problem, this is what we have. So this is the equation for the log likelihood of this particular data set D. So to make this notation simpler because of the A's and the B's, what they do is that they actually separate the summand into two separate things. So the first thing is that we're going to sum over I in D of A. And then the next one, which I'll do below, is that we're going to sum over I in D of B. So this term is the probability in this equation, probability of YA, which is just equal to, well, the log probability of Y is equal to A is just this, plus the log of this term, which we said is distributed geometrically. One. And then this second term, which we said is distributed exponentially. And we would repeat the same equation, but for this, so we would add these two things. This is equal to this, where we would write the same thing, but instead of all the A's, we would put the B's.
I was just confused because they use like theta A, they say like log likelihood of theta A, and not the whole equation.
Oh, so they're basically just decomposing this into 6 different sums.
No, I know, but like you were putting the whole equation down, you're putting the whole probability down, as the log likelihood, but they're saying log likelihood of like theta A. It's only theta A. Like the way they denoted that.
So the part where
They say log likelihood of theta A. That means like the whole equation, right?
log likelihood of theta A, yeah.
Like the notation was kind of
Okay, yes.
Don't you have to say log likelihood of the whole PR equation, not just like theta A?
Yeah, I think it just might be a weird notational thing that they did there, yeah. It's not like we were expecting the people who took this exam at the time to decompose it in this way. It was just more of did they do this? Okay. So then it's asking to derive the expressions for the maximum likelihood estimate of the parameters of your model for theta A and B, and then for lambda A and B. And so does everybody understand what maximum likelihood estimation is? Would anybody like me to explain it? Okay, I'm not seeing anybody nodding, which is surprising. Okay, so in order to find the maximum likelihood estimate for theta A and theta B, what we're going to do is that we're going to take the partial derivative of the likelihood term. So if we're just going to call this the log likelihood, what we need to do is that for the log likelihood, we're going to take the partial derivative with respect to theta A. So I remember when I did this in the recitation that actually computing theta A in this closed form, it was kind of tricky and you had to do some adding by one math and that sort of a thing. And so if you see this in the exam, we're either going to make the derivatives and solving for it easy enough that it's not going to be a stressful part, or we're actually just going to explicitly give you the equations. Yeah.
So, I mean, unless other people want to do this, like I'm fine. The data and the other one, yeah. So the first two are fine.
Uh-huh.
And just explain the third one, why gamma? Because like for gamma, they didn't use black likelihood. They just said, it makes sense that is the answer, but to do black likelihood, we wouldn't get the same thing.
So the gamma, so we're talking about the prior, which is P of y.
Yeah.
And if we assume that this is distributed from a multinomial, or because there are only two variables, I think this is also the Bernoulli distribution. If you assume that this is a Bernoulli distribution and you take the partial derivative of this with respect to the gamma A and the gamma B, and you make sure that gamma A and gamma B add up to 1, it will be exactly as it says here.
But don't we use the equation that we have for P of y? Like for the conditional ones, you have the distribution, and you use that distribution to do the log likelihood.
Yeah. Yeah. Yeah.
Why can't you do the same thing for P of y? Because you also have that distribution for P of y.
Because what value for theta, or what value for gamma is going to maximize this?
Well, I mean, not zero.
So why did you say 0?
Well, if you do,
So what I'm trying to point out is that if you set theta equal to 1,000,000, that's a really big value. But theta could, and you keep, gamma. If you set gamma to 1,000,000, you can actually just increase the value of gamma. And so the reason why that just taking the partial derivative with respect to these doesn't work out exactly is because you have to ensure that gamma A and gamma B sum up to 1.
you have to write both equations and add them to
Yeah, I think, yeah, so there's the, I think the way that you have to do it is that you have to introduce these Lagrange multipliers because you need to make sure, right, so it's complicated. But it works out that these are the MLE equations for that, yeah. Okay, so for 3, we're given some data. We have the MLE equations for theta and lambda and gamma, and we just plug them in, and we solve for those values. Yep, sure. Then for B, we've seen this when I had it before, where you output alpha, predict y is equal to A if that fraction, which is the joint probability of x and y under the naive Bayes assumption, if that fraction is greater than 1, then probability of A is equal to larger than B. Okay. Okay, let me just do this last page, and then I'll probably wrap up. So based on the parameter values which we calculated, we're just asking you to compute this. And so we're asking you to compute the probability y is equal to A, given x1 equals 2, x2 equals 16. And so the way that you should do this is that you should use Bayes' rule to flip them. And so it'll be the probability of x1 is equal to 2, x2 is equal to 16, times the probability, given y is equal to a, times the probability of a, y is equal to a. And all of this is going to be divided by the probability of x1 equal to 2, x2 is equal to 16. And this is the numerator for this equation, and then you do the same thing for the denominator. These two terms are going to cancel because they're in both of them. And then with this, because it's we're assuming that for this problem it's a naive Bayes assumption, we can just say that this term is equal to the probability of x1, probability of x2 equals 16, y is equal to a. And then obviously this gets carried along. And then you would do the same thing for the denominator. And then for this particular problem, it's asking you to use the values which we estimated before and just plug them in and solve. And then for the last problem, D, it's just asking you for this particular point, what is the value going to output, and you can use the equation that you derived in B to do that. Cool. Okay, I can stay after for a few minutes. Sorry I screwed up the SVM thing, but if there are any particular questions that you all have, you can put those on Piazza, and I'll try to look at it between now and the exam. I probably will. I don't remember if there are office hours on Sundays. I will probably have my office hours for 1 hour from 10 to 11 on Monday before the exam, but then I have to get prepared for the exam, so I'll end them exactly at 11 so I can go and get set up. Cool. Oh, sure.
Great class.
Yeah.
You'll see me on Monday probably, but yeah.
I hope I'll see you on Monday.
No, I mean at 10.
Oh.
I just have one question about the time parameter estimation for short questions.
In the which
Sorry,
exam?
reductive and false system. The next one. So this, like, how did we get these parameters? I don't know, like I'm not very good with the parameter questions.
Okay.
Maybe getting this with